get started with the Spacy workshop. So these different kind of NLP libraries, for example, last week I introduced you guys with NLTK. So it is very similar to NLTK, but before starting with the demo, I'll just give you a brief overview about this Spacy library and how exactly is it different from NLTK library. So it has a pretty straightforward installation to, like, if you guys want to have a hands-on or practice, then you can also install it in your local machines. Or if you are like doing it on Google Colab, just like me, then it's pretty easy to import. So the basic difference is like there are like mostly there are similarities. For example, both support all the kind of text processing, string processing, and most of the statistical modeling techniques. So it's carried by both of them. NLTK has a bigger corpus of languages, whereas Spacy as of now has seven statistical models for seven languages. And there is kind of difference in the treatment. Like NLTK acts as more of a string processing library, so you input it a string and it returns a string, whereas in the demo we will see that Spacy follows a much more object oriented approach. So you might feel NLTK to be more Pythonic, but Spacy, because of this OOP approach, it is more used in industry. And the most important being that Spacy has a support for word vectors, whereas NLTK does not. So in the demo towards the end, I will show you what exactly like you guys are already familiar with it. I'll just show you how to use it with Spacy. And generally, Spacy has a better performance as compared to NLTK. So that is another one more reason why it is more popular in industry. And NLTK is more towards like if you want to have some research driven projects and all. So you can see that the timing of Spacy is shorter as compared to NLTK, except for sentence tokenization. So you can research about it, that why it is so. It is basically because of some like Spacy handles this in a different way by creating a graph semantic of the sentence, whereas NLTK does it via a more straightforward approach. But generally, you can see that Spacy performs much faster. So yeah, as I just told that Spacy is more popular in industry in the production environment, whereas NLTK is a go-to-go library, good to go, like if you just want it for your personal projects or something like that. So I'll just switch over to the demo. So yeah, starting with the Spacy library. You, you can just, for example, we'll be dealing with English. So just import as it is shown spacy.lang.en. En stands for the English language, and from that import English. And over here in the second line, NLP equals to English, we instantiate a NLP object. There are different ways of instantiating it. I'll show you that later on in this workshop. One of the most straightforward ways this. So this NLP object that you can see, mostly it is given the variable name as NLP. It contains all the processing pipelines, the language rules for tokenization, similarly like it was in NLTK. So it will become more clear by if I give you an example. So we pass this object a string. So over here, I have passed, suppose, hello world. Obviously, it's your choice if you assign this string to a variable and then pass that single variable to the NLP object. And over here, you can see how we can get the tokens. So this is the first preliminary step of tokenization. If you guys would remember in NLTK, I showed that it is like dot token words, something on those lines. Whereas in Spacy, we get the tokens like this. Like we iterate over the NLP object. So over here, like I have assigned this to doc variable and then just print the text. So it will print all the tokens. So moving on, over here, I just printed the whole doc object. So you can see it's the same as the string. And you, just like Python lists or strings, you can access it by slicing, sub-slicing, indexing. So it acts as a very similar, in almost identical way as in a normal Python list or string would. So if I just access doc1, it will give me the second word, that is world. And similarly, you can um, get a span from the doc object. So for example, over here, this is just to the left of the colon will be the start index, and to the right is the end index. The end index is not inclusive. So from here, I have done till 2. So it will give me hello world. That is hello 0, world 1, and 2 is the exclamation mark. But since the last start end index is not included, so it will give me from 0 to 1. 0 hello and world is 1. So hello world is returned in the print statement. And just similar to the above, like just how you retrieve the tokens by token.text, we can retrieve some other attributes as well. Like if you want to get index, you do token.I. Over here, like we were printing in the for loop, and here we are just appending it to a list and then printing the list. So this is the same as we did earlier, token.text, but it's just that we are appending in the list and printing the list. So dot text, as we just saw earlier, it returns all the tokens, hello world and the exclamation. Dot is alpha. It is returns a boolean that whether the return token is alphabetical, alphanumeric or not. So hello world is alphanumeric, so therefore it returns true, and the last exclamation is a punctuation, so it returns false. In dot is punctuation, that is underscore punct. You can see that it returns whether the token is a punctuation or not. So the first two, hello and world, is false, and the punctuation is returned as true. And similarly, the dot like num shows whether it is numeric. So over in this text, there are no numbers, so everything is false. And many other such attributes are available, which you can always go through the documentation, and it's a need-based document searching that you can do. Now coming over to the more interesting part, that is the statistical modeling. Now, since you guys have been introduced to some of the modeling aspects in your video lectures, in Spacy, we can explore like how you actually implement these modeling and how that all training is taken care under the hood. So for this, you will have to download. Uh, there are different models on which this Spacy model is trained. So for example, over here, I downloaded, for the next few examples, I had downloaded the English Core Web Small Model. Now, EN stands for English, SM stands for small. There are other two models where SM is replaced by MD, which stands for medium, and there is one more model, large. I'll tell you the uses of those models as well in later in this workshop. And web is because it is trained on web text. So this whole corpus of web text, this model is trained on that. And we just downloaded that model, and we will use that model to do our own predictions. We can also retrain, not retrain, but finer tune the model by adding some more examples and training on our local examples, maybe. So that you guys will get introduced maybe in later workshops when you are more acquainted with neural network training and on all those areas. So this is how you download the model. I have commented it since it's already downloaded in my collab notebook. So, and then like there we instantiated the NLP object with English. Over here, this is how we load the model. We import a Spacy and Spacy.load this model name. And prior to loading, you have to download this model. So this model contains all the weights, binary weights, which is used to make predictions. So it's basically a neural network that has been trained on a large corpus, and that model you have just downloaded it, and we will be using it for our own purposes. So there's like no need of you retraining on a very large corpus again. So let's see how we can use this model in our like some of the examples. The most basic being pause tags, that is part of speech tagging. Now it's a very basic yet interesting example. So let's see this. So suppose over here, like just I instantiated the NLP object and I passed the string, she ate the pizza. In this example, I've passed the string and assigned it to a variable dog. Now, just like earlier, just as I have shown you, we get the tokens. And along with token.text, I also print the pause underscore. That is a part of speech. In Spacy, there's a convention that you will also see later on that in most of the functions that returns a string, there is a underscore after that. So that's why it's pause underscore. So you can, it's just a like kind of info that I'm giving you. So she, and it returns a pronoun. Ate is a verb. The is a determinant, and pizza is a noun. So you can see that the predictions are correct, and in this simple text, it has correctly predicted and identified which word belongs to what part of speech tag. So moving on, there are other dependencies that you can get along with the pause tags. So just like in the earlier example, the same example we are using. And now apart from that token and pause tag, we are also printing the dependency and head. So that is done by .dep underscore and .head. So what does .dep shows? It shows what is the subject and what is the object in the whole sentence. For example, in the text, she ate the pizza, she is the subject and pizza is the object. So token.dep prints out that. And head is, it just gives you a more, like you can visualize this sentence and it gives you a much more like relation amongst the words. For example, she points to the word eight. So it's eight. Eight is a root word. So there's no more pointing. It's a root verb. The points to pizza because pizza is the main object and the is pointing towards that. And pizza is pointed back to eight because the verb eight is acted on the noun pizza. So this is like kind of a graph that you can make. So these are some pretty useful things that you can do with this Spacy model. So yeah, you can read this. This is what I have said. And yeah, these strings that are returned, if you don't understand what exactly does this signify, there's a function called spacy.explain. So you can just copy and paste in this. For example, if you don't know what this DET stands for, just pass in DET and it will show that it stands for determiner. And DOBJ is direct object. Then from pause tagging, let's move on to name entity recognition. That is again quite a useful thing. And all this takes out a lot of training, but you can see that how the simple it becomes for you just by downloading the pre-trained model. So you have downloaded and that too, it's a small model, not a big model. You have downloaded the English small model and you are just using it for your own predictions. So over here, the doc, again, I have instantiated the NLP object and passed in a different string, doc.ents. Now, what is this? This lets you access the named entities predicted by the model. So the model has a .ents, that is, which stands for entities. You access that. So we iterate over the doc.ents, and then we get its text and its label. Now, what exactly does that name entity signify? That you can get by ent.label followed by an underscore. So as you can see, it correctly predicts that Apple is an organization, UK is GPE. Now you don't know what does GPE stand for. So I do spacy.explain GPE. And it basically stands for geopolitical entity. So it's like countries, cities, states. So it predicts UK as GPE, $1 billion as money. So you see that like it's quite an accurate prediction because it does not signify apple as a fruit. Rather, correctly, as per the sentence, it shows it as an organization. So this is the beauty of how the Spacy model has been trained. So yeah, this was the name entity. Next, moving forward to rule-based matching. So what exactly is rule-based matching? You guys have already done this using regex. So you can like kind of imagine that rule-based matching in Spacy is like the upper version of regex. Like it's maybe more simpler and more handy to use and with much more functionalities. So it's like a very advanced version of regex. So how to use that, I'll just show you. So it is basically like if you have to match patterns in a match tokens, patterns in a text in a corpus of sentences, then this can be very useful. So how exactly do we define token texts? So it is done in a list. So it's like text, iPhone, lower means lowercase, lemma means the root word. So what exactly these things are, it will become more clear with the examples. So I'll just show you the example directly. So over here again, we have loaded the small model and I have created a matcher object. So initialize the matcher object on nlp.vocab. Now nlp.vocab is a like entity for shared vocabulary. I'll just tell you, we will revisit this nlp.vocab in more detail in our next section. But as of now, just remember that matcher object is instantiated on nlp.vocab. NLP is the object and vocab is the entity that we are using to instantiate. And the pattern, like which pattern do we need to match, that is passed in a list. So over here, we are searching for two tokens, iPhone and X. What is iPhone? It's a text. So this is how you define the um, pattern. So in a list, and the first part, the entity in a list would be a dictionary, where the key is what exactly the value is. Like for example, here it's text. So key is text and its value is iPhone. And then we use the matcher.add function to add this pattern in the matcher object. So what are the arguments? The first is you can say a unique ID. So iPhone pattern, I have given a name to this ID. Second is an optional callback. You can look more about this in the documentation. It's an optional argument. And the third and the argument is the pattern that you want to find. So over here, I have passed the pattern. Now this is the doc object, this string, upcoming iPhone X release date leaked. And then I call this matcher that I have added over here, added the pattern functionality. I call this matcher on this doc object, and I have assigned this to a variable matches. Now, if you print matches, it will give you a list of tuples. So over here, you see that the first is a unique ID of the match. Then the second argument that you get in the return of matches is the start index, and the last is the third index. So you can see it returns 1 and 3. The 1 stands for iPhone and 3 is the release. But remember that don't get confused with 3 that it should be 2, because the end index is not included in Python list or strings when we iterate over it. So it will get more clear when I show you this section. So this is the matches variable. I iterate over the matches. So match for match ID, start index, and end in matches. I just span the matched object. So it should be iPhone X, right? So here, this is the start index. So I go from doc start to end, and then print this variable, that is match span dot text, and you see that it returns iPhone X. So this was just for our verification. So the matches variable gives the start to end index of our match that was requested. So you can just go over through this all over this again. And now I'll just give you one more example about this, like how we can add in more functionalities in this matching. So suppose if I want to match along with more lexical attributes. So over here, you see that these are the pattern. This is the pattern that I want to match on. And there are different tokens that I have passed on to the list of this pattern. So the first is digit and it should be true. So this is Boolean. The second is lower FIFA. You can guess that why I have used lower and not text. So because if I use lower, it will generalize. So it won't differentiate if in the actual text, the FIFA F is capital or all the letters are capitalized in uppercase. So it will first put them in lowercase and then find the match. So it will standardize. So that's why I have used lower and not text. So what I basically want to find is FIFA World Cup, and it should be preceded with a digit and succeeded with a punctuation. So you see, this is kind of a complex match pattern that I'm defining over here. And then this is the string that I have passed in the doc object, 2018 FIFA World Cup. So it should match to the first 4 to 5 words. So 2018 is a number. So is digit true? The first condition holds true. Second is FIFA lower. So it will match with FIFA, even though it's capitalized. But remember, we have put here over the key as lower. So it was standardized. Then World Cup followed by a punctuation. And this is the punctuation, the colons. So again, we will add this using the matcher.add function. Pattern 2 is a unique pattern ID followed by a optional callback. And the most important, the pattern argument. So here the pattern 1, I have passed that. Again, call this matcher on the doc object and printed matches. Then you see that I get the, what do we say? The match return indices. Now ignore this multiple values because this was because I run this cell multiple times. So that's why it has generated the same result, but with different match IDs. So just ignore this part. You can just focus on the first attribute. So it is from 0 to 5. So again, if I print this from doc start to end, start is the 0, end is 5, and in matches, and I print the matched span from start to end, and it successfully verified. We can verify that it successfully returns what we had included in the pattern match pattern. 2018 FIFA World Cup followed by a punctuation. So this is the matching part, and there's a lot more to it. Like there are, you can again, for example, if I show you one more example, the text is I loved dogs, but now I love cats more. And over here, I have passed in lemma. Lemma stands for the root word, that it will, even if it's loved, loving, it will match with the root word love. And a noun. The second one is the key is pause, that is part of speech. And what we are finding? A noun. So we are finding love, that is the root word of that word should be love, followed by a noun. So can you guess what it will return? Just think. So yes, it will return two entities. One is loved dogs because the root of loved is love and followed by a noun, as well as love cats. So therefore it returns two, that is from 1 to 3 start, and another one from 6 to 8. The 6 to 8 resembles love and cats. And when we verify this by printing, there you go, loved dogs and loved cats. So you see, this is how this is useful in string. If you want to find patterns in a long text, long string, long corpus. And you can see that the functionality is very much similar to regex. So you guys can look over this on your own, that how you can add more functionalities to this by using operators and quantifiers. So this makes it much more flexible, though it adds into the complexity. So these things should be used carefully. And so yeah, you can look about this on your own. And then I told you that about the dot vocab, right? That we added dot vocab over here. So, okay, I can see that there was one pop-up in question, but I can't like jump to it without stopping screen share. So I'll just address all these questions at the end. Zoom makes it difficult to see the chats while I'm sharing screen. So yeah, I'll just show you like if you remember in the start I had just showed that you use NLP.vocab. So that is actually a data structure that is used in Spacy. So what exactly it does is to while training to save memory, it doesn't store the words as strings but as hash values. So each string a word is associated with a hash ID. So every time the same word is called, you need not store the same word twice. That single hash ID will resemble to both the words. So it works on the principle of the dictionary data structure that you have in Python. So you can look into this, like it's something for your information, like how Spacy stores words under the hood. For example, if you print nlp.vocab.strings coffee, it will show you the hash value. And if you again pass in this hash value, it will give you the word coffee. So these are some of the details. Now I'm coming to the most important, since we can see that we are running out of time, I'll just quickly come over to the most important part, word vectors. Now this is the part that is not supported by NLTK, but it is supported by Spacy. But for this, for word vectors, you will have to download a more larger model because word vectors is not supported in the small model. So as I had told that there are different models, you can see this model has English Core Web underscore MD. MD stands for medium. So medium and large models support word vectors. So you will first have to download this, and then you will have to load this model. And when I load this model, then I can play with the word vectors and like finding the similarity between two documents. For example, I have just show you an example quickly. So I passed in one sentence, I like fast food, and the second sentence is I like pizza. And then we do a similarity between these two sentences. And you can see that it returns a kind of high similarity because maybe pizza can come under fast food. And so it has like given that these two sentences are quite similar. 0 being the least similar and 1 being the most similar. So 0.86 is like quite close to being very similar. Then similarly, you can compare two tokens. For example, over here, I like pizza and pasta. I am comparing pizza and pasta. So token 1 is pizza, token 2 is pasta. And you see that it somewhat gives a higher similarities. It's kind of like relating that both are food items, both are kind of Italian, both are like fast food. So that's why it has given kind of a high score. But since both are different food items, hence it's not complete one. And you can play around with this by different, like you can match a span in this cell. You can see I've matched a span, so I'm not matching the entire text but just matching a part of text, pizza and pasta, with the word this whole sentence. And you can see that it gives a mid similarity score because it's like we are matching pizza and pasta with McDonald's sells burgers, but MACD doesn't sell pizza and pasta. So it's like it's an interpretation that you can make. Um, so this is like you guys have you might be wondering that how it does back, what's the back end of this in Spacy. So all these words, all these tokens are represented as multidimensional vectors. And how that is achieved, that is there's different algorithms. One that you know is word to vec. There's already a video tutorial on that. So this is how even Spacy does it on word to vec. And how do we use the similarity? So by default, Spacy uses a cosine similarity. And I guess you have a provision where you can change this similarity, like you want to have some different kinds of similarity, then you can pass in an argument. I guess it does that. So yes, so suppose I want to see the vector, like I just told you that it uses word2vec and converts the entire token into a vector. So for example, over here, this is the text. I use the word banana and just print its vector. So this is the vector, and you can play around with the vector. I just printed the shape of the vector. It's 300 dimensional. And the dimension does not depend whether the vector is a word or a entire text. Even if I pass in the entire text and print this shape, it's still a 300 dimension. So even the entire text has a 300 dimension. So yeah, this was the word to text, the word vectors in Spacy.